This lecture is going to cover the simple gas laws. You're going to want to make sure you have your objective sheet and your calculator with you. Before we start talking about the laws, we want to discuss the kinetic molecular theory. Now, the kinetic molecular theory describes to us the behavior of gases. So how do gases behave? Now, we know already that gases do not have a definite volume and they do not have a definite shape, but we want to talk about that in a little bit more detail here. So the first thing is that gas particles are constantly in motion. Now, their motion is random, but it is in the form of a straight line. So I'm going to have a gas molecule here, and it's going to continue to move in a straight line until something hits it. I have another gas molecule here. It's going to continue to move in a straight line until something hits it. Now, the direction in which it goes is random, but it is going to be continuously in a straight line. Now, gas particles do not attract or repel each other. So these two molecules here, they're near each other, but they're not going to attract, so they're both not just going to move in towards one another. They're not going to repel, meaning they're not going to just go off into another direction because they are near each other. They're going to act on their own. So they are going to act independently. Remember that there's a lot of space in between gas particles. They will expand and move as far apart as they can. So that is one reason why our volume is not constant, is because your gas molecules are constantly moving in opposite directions, and what that opposite directions will allow for is for there to be a lot of space between your particles. Now, something we're not going to get a lot into, but the average kinetic energy within a gas sample is going to be proportional to the temperature, but it's going to be proportional to the temperature in the units of Kelvin. Now, I want you to remember that your temperature needs to be in Kelvin. We're going to go over that multiple times, but temperature, we're looking for it to be in Kelvin as we go through each of these problems. So one thing we're going to talk about is pressure. Now, pressure is the force that is being acted upon the gas per unit area. So within a defined area, or what will be your volume, how much pressure or how much force is being acted upon with those gases. Units that you will see for pressure, you may see Pascal, which is abbreviated as PA, atmospheres, which is ATM, torr, which will be written just as is on here, is TORR, millimeters of mercury, or pounds per square inch, which is PSI. You may be familiar with this unit of PSI if you have ever dealt with pressure on tires. So that's where that comes from. Two equivalent statements you're going to want to be familiar with. 760 torr is equal to 1 atmosphere, and 1 torr is equal to 1 millimeter of mercury. So I guess we can write another one here, is that 760 millimeters of mercury is also equal to 1 atmosphere, since your torr and your millimeters of mercury are equivalent. So we're also going to be discussing volume and temperature. So just a reminder, this should say units of volume. Let's change that. Units of volume are going to be milliliters, liters, millimeters cubed, centimeters cubed. Now the unit is not specific, but it needs to match your problem. So if you have one volume in milliliters and you have the other one in liters, you're going to have to convert one or the other. Maybe you get your final answer as centimeters cubed and I want you to convert that to milliliters. You're going to have to do that. But there's not a specific unit of volume that you need to carry throughout the entire problem. However, with temperature, there is. Temperature has to 100% be in Kelvin when you are dealing with gas problems. So if you're given the problem in Celsius, you're going to want to convert that. So if you remember, Kelvin equals your Celsius plus 273 degrees. So you can go ahead and make that write that equation down if you do not know that already. But we're going to be using this a lot, and it will not be provided for you. All right, Boyle's law. So Boyle's law is the first gas law we're going to talk about. This is the pressure volume law. So it states that the volume of a gas when at constant temperature. So this means that our temperature is staying the same throughout this entire situation or scenario. Will vary inversely with your pressure. So if you remember doing the specific heat deriving, so how you created that equation for solving for energy with your mass and your specific heat and your temperature change, if it is inversely proportional, we know it looks like this. So that's your inverse. Oh, then your pressure, which means that your pressure is also inversely proportional to your volume. Now, how do we write this? When we're writing this in equation, it's going to look like this. P1 V1 equals P2 V2. So this should look familiar for several reasons. One, it looks very similar to your dilutions equation. And then it also looks familiar because when you were trying to figure out if my mass and my temperature change were inversely proportional when you were solving for a specific heat, we ended up multiplying them. So there is your first equation. You will not be given these equations, so you need to be familiar with them. So any of these, I'm going to box all of them just like this. Make sure that you know those and you're writing those down. Okay, so let's write that equation down because we're going to do a practice problem with Boyle's law. The initial volume of a gas was 500 milliliters at 760 torr. The volume is compressed to 450 milliliters. What is the new pressure? So let's just organize our variables first. So what is the new pressure? That means we're searching for our pressure 2. If you're looking, it says the volume is compressed to 450 milliliters. That's our second volume. That's what the volume we're ending with. The initial volume of a gas, the starting temp volume, is 500 milliliters and 760 torr is our initial pressure. So we're searching for our, or solving, we're not searching, we're solving for our second pressure here. So now all we have to do, plug our volume or our variables into our equation. So we have 760 torr or times 500 mLs equals 450 mLs times your V2. So the first thing to do is just solve this algebraically. So we're going to multiply our 760 times 500, and that's going to give us 380,000 equals 450 times your V2. Remember that this is in mLs. I should have put that on there. Your units on this side are going to be torr times ATM, or times milliliters, sorry. So now to solve for this V2 here, we just need to divide each side by 450, and that gives us 844.44. Now what's my units? Well, milliliters canceled, so we're left with torr. So now looking at the equation, or the statement that we looked at before, said that our pressure and our volume are inversely proportional. So what happened here? My volume went down. My volume started out as 500 and it went down to 450, which means that my pressure should inversely means it should go up. So I had 760 and I'm ending in 844. So just double check yourself. Make sure that your answers are making sense with the statement that you are given at the beginning. Next law, Charles' law. This is going to be dealing with temperature and volume. So Charles' law states that the volume of a gas at constant pressure, meaning our pressure is staying the same, it is not changing, is directly proportional to the temperature. So my volume is directly proportional to my temperature, which means my temperature is directly proportional to my volume. So as my temperature goes up, my volume goes up. Okay, so now direct is going to be a division. So V1 over T1 equals V2 over T2. Second equation, red and box, this is what you need. So I'm going to write it up here if you didn't get it before. V1 over T1 equals V2 over T2. Okay, so what volume will nitrogen gas occupy at 27 degrees C if the gas occupies 400 mLs at a temperature of 0 C? So we're looking at volume 1, temperature 1, volume 2, temperature 2. So if the gas occupies 400 mLs, that's my volume 1, at a temperature of 0 degrees Celsius, that's my temperature 1. What volume will the nitrogen gas occupy? That's my volume 2, and that's what we don't know, at 27 degrees C. Now, what do I have to do with these C's? I need to make them into Kelvin. This is going to be 273 K, and this is going to be 300. Okay, now it's time to plug them into our equation here. So we should have 400 ml over 273K equals my V2 over 300K. Now, just thinking to our statement about Charles' law that they're directly proportional. So look at our temperature. Our temperature is increasing, which means that we expect our volume to be increasing. So let's make sure that we get that. Okay, just go ahead and do the algebra in this. 400 divided by 273. And then we're going to multiply by 300. Should give us an answer of 439.56 milliliters. The Kelvin canceled. So my temp went up, my volume went up. So it's just plugging into these equations is really what we're looking at here. Being able to recognize which equation you need to use and what variable represents which number in the problem. Next law is Gay-Lussac's law, which is going to deal with our pressure and our temperature. This law tells us that the pressure of a gas, which is at a constant volume, so our volume is staying the same, it is not changing, is directly proportional to the temperature. So your pressure is directly proportional to temperature. Your temperature is directly proportional to your pressure. So as my T goes up, my P goes up. So this is going to look very similar to the equation that we just did, where our volume and our temperature were proportional. Except now we're replacing that volume with our pressure. P1 over T1 equals P2 over T2. Third equation. All right, looking at a practice problem. Put our equation up here. P1 T1 equals P2 T2. Determine the new pressure when a gas at 1 atm is heated from 20 degrees Celsius to 30 degrees Celsius. So let's go ahead and write out our variables. P1, T1, P2, T2. Determine the new pressure, which means we're looking for our P2. When I gas at 1 atm, that's my first pressure, is heated from 20 degrees, so we're starting at 20, to 30. What's the only thing we got to do here? We got to change these temperatures, right? We've got to put those into Kelvin. So this is going to give me 293 K, and this is going to give me 303. Make sure that you are doing that. That needs to be done each time. Okay, let's put everything in our equation. My P1 is 1 atm. My T1 is 293 K. My P2 is unknown. And my V2 is, or T2, sorry, is 303. Okay, that should say 303, not 330. All right, so we're solving for this P2 here, so let's do the math. On that left side of the equation, we have no variables, so let's do the math there. We have 1 divided by 293, which gives me 0.0034 atm over K equals P2 over 303K. Now to get that K on the other side, I'm going to have to multiply. I'm left with 1.034. My units of K cancel, which leaves me with atm. Now let's check this. Does this make sense? My temperature did what? It increased, which means that my pressure should also increase. Started at 1 atm, ended at 1.034. So it did go up. Last thing here is the combined gas law. Now, there are going to be times where you don't have a constant temperature. Your temperature is changing, but your volume's changing and your pressure is changing, which means we can't use any of those 3 equations that we just looked at. We have to combine them as one. So if you remember, your pressure and your volume were inversely proportional to each other, but both of them were directly proportional to your temperature. So all we're doing here is combining our equations. So here's what we got. This is your 4th equation that you need to be familiar with. All right, let's take a look at this last problem here. So we have P1V1 T1 equals P2V2 T2. Okay. 500 liters of gas is prepared at 700 millimeters of mercury and 200 degrees C. The gas is placed into a tank under high pressure. The tank cools to 20 degrees Celsius and the pressure is now 30 atm. What is the volume? Now we're going to have a few more variables than before. So this first sentence tells us everything we need. 500 liters of gas is prepared at 700 millimeters of mercury and 200 degrees C. So 500 liters is going to be my volume. 700 millimeters of mercury is my pressure. And 200 degrees Celsius is my temperature. Now looking for our P2V2 T2. The gas is placed into a tank under high pressure. That doesn't give us any information. The tank cools to 20 degrees Celsius, so that is my temperature. And the pressure is 30 atmospheres. The only variable I don't have is my volume, but that's what we're solving for. Okay, before you start a problem, what should we do? We got to make sure our units are okay. So what do we know about our temperature? It needs to be in Kelvin. So this is going to give me 473 K. And this is going to give me 293 K. Volume, I'm solving for the volume down here, so we're just going to stick with liters up at the top. But now look at your pressures. We have 700 millimeters of mercury and 30 atmospheres. Let's go ahead and convert those. Remember, very, very early on, I gave you an equivalence statement that was 760 millimeters of mercury is equal to 1 atmosphere. So we could go either way. We could convert the millimeters of mercury into atmosphere, or we could convert the atmospheres into millimeters of mercury. We're just going to convert into atmospheres here. It doesn't matter which you use, though. So just using some dimensional analysis. I know you all love it so much. 700 divided by 760 is going to give you 0.921 ATM. So we don't need this anymore. Okay, so now we have our values. We're just going to plug them into our equation and then solve. So our P1 is 0.921 ATM. And we're multiplying that by 500 liters. And that's being divided by 473 K. And that equals, our pressure 2 is 30 ATM times your V2, which is what we're solving for, divided by your temperature 2, which was 293. All right, let's solve on the left side so we can get all those numbers put together. 0.921 times 500 divided by 473. So on this side we're going to have 0.9736, and my units, nothing cancels. So we are going to have ATM liters over K equals 30 ATM times V2 over 293 K. Now we are solving for this variable right here, this V2. Trying to get that by itself. So we got to move that K over. So we're going to multiply each side by 293 Kelvin. So now we have 285.26 ATM times liters, because my K's cancel, equals 30 ATM times your V2. Now to get my V2 alone, I'm going to have to divide by 30. Which leaves me as my V2 equals 9.51 liters, because my atmosphere canceled. Now, as you are doing these problems, sometimes we are tempted to rearrange the equation in our head and then put the values in. My suggestion is use this equation. Plug your values right into that, then rearrange. Use this equation. Plug your values right into that, and then rearrange. Same here. Plug them in, then rearrange. Plug them in, then rearrange. Do not try and rearrange equations in your head. Plug them into the equation first, and then rearrange them to solve for the variable that you are looking for. If you have any questions, as always, please let me know. Go ahead and work on some practice problems, and good luck.